In the last video, we created Conway's Game of Life and wrote a simple 2D engine to render it. Before we get started loading bitmap images, I want to clean up a bit of that OpenGL code to make it more consistent and reusable. This includes moving our screen translation functions into the engine, because I don't foresee us really changing that too often, and fixing our engine's draw loop to use the glut post redisplay function and check if a window exists before attempting to render it. Also, let's put our OpenGL clear and flush routines in the engine as well. Now that we have our game engine updated, let's put the foundation for loading a bitmap file into our program. We're going to load this from command line, so we need to do an argument count check first to make sure we actually provided the file name in our command line arguments. From there, we can build out our bitmap, CPP, and H files to isolate the labor of loading a bitmap. Since we're reading data from a file, I find it best to load it directly into memory and then close the file, so that we can avoid other programs modifying the file while our code is running. It's relatively simple to do. We get the file size, then read it into memory, and on my platform, the unsigned car is 1 byte, so we can load the file into a set of bytes represented by an array of cars in memory. From there, we can build out our definition structs that represent our overall bitmap image and an individual bitmap pixel. While writing code, I think it's best to write the functionality you wish to see before writing the implementation. This gives you an overall goal your code should accomplish before getting into the weeds and problem solving the implementation will produce. Also, I think it's very important that we write code to explicitly free memory we allocate with malloc or new. Every time I write a malloc or new statement, I try and write the corresponding free statement or delete statement just to make sure I don't create any memory leaks, and I make sure that the memory that is allocated at least has the proper responsibility of removing itself or designating what other part of the program needs to remove that memory that's been allocated. Before we actually get into reading the BMP format, we need to understand how the format is structured. Here's an image of the overall structure of a BMP, and it has these 4 main parts. The bitmap header, which stores general information about the file. The dib header, of which there are a variety, that stores the detailed information about the image, like pixel sizes, etc. The color table is optional, and in this video we will not be using it, but it is essentially a pairing of index to an RGB color value that the main image data can reference to reduce the amount of file size necessary for the colors. With 24-bit bitmaps, the colors are stored in the pixels, so the color table is not used. That brings us to the pixel data itself. Pixels are packed into rows in the file. Each row must be a multiple of 4 bytes. So for images with a width that is not a multiple of 4, say 10 pixels, there's a padding added to the row data that we must account for. How the pixel data is stored is different depending on the number of bits allowed per pixel. For 24-bit files, which we are starting with, each pixel is 3 bytes, 1 byte per color, in the order of blue, green, and red. Let's dive into the code and read this format ourselves. Let's write our read BMP function that can actually read these 2 headers that we've just gone over. We're only going to focus on the type of dib header that is common in Windows, and I haven't actually seen a bitmap file that doesn't actually use this header. I believe it's called the bitmap info header, and you can find more information about it on Wikipedia. The actual bitmap header parts are different depending on which header you're looking at. We have in our first header size and offset as our most important features that we really want to read out of it. The dib header has a dib size, which actually represents the actual dib header type we want to read. Then we have pixel dimensions, number of color panes, color depth, compression method, number of colors inside of the color pane, and then we're going to go ahead and add a few extra calculated values like row size, array size, and the actual pixels that we're going to store for our bitmap. Now it's just a simple matter of reading the proper number of bytes at their offsets into our memory, from our memory into our actual header that we're building out here. Test is always the string BM, and it's helpful to be able to see what we're rendering with that. Reserved is actually for the creation tool of the bitmap as optional place where you can store data. Offset is the location of the actual image data in the file, so that's important to know as well. We want to check that the div size is actually 40 because this represents that this div header is the bitmap info header that's common in Windows. From there, it's just basically reading in the data as memory locations and byte offsets into our div header and writing all that with memcopy that we need to load from our C header string. Some of them are 4 bytes, some of them are 2 bytes, but it's relatively rudimentary to get that information loaded. We're not going to support compression methods at this time, and I haven't seen a bitmap that uses it, though they're out there, and the documentation on how to decompress a bitmap is available on Wikipedia as well. We do have the color palette that we would like to be considerate of, but the bitmap 24s don't actually use the color palettes because all the color data is stored inside the pixels as well. So we can just say that's unsupported as well. We want to check that our color depth is 24 because that's all we're going to load to start with. So let's read the actual pixel data into our pixels that we have inside of our image that we're building out here. Remember that row size needs to be a multiple of 4 bytes. So with a little bit of integer math, we can round up the pixel width to the nearest multiple of 4. Then we want to calculate our array size, which is literally the width of the image times the height of the image, so we get the proper amount of pixels. From there, we just loop over the number of pixels we want to actually read. And we're going to load the row data into a piece of dedicated memory so we can make sure we get all the padding with it. Now that we have the row data loaded, we can go ahead and loop over the actual pixel values that are stored in each row. We're going to do this in groups of 3 because there's 3 colors. And those colors are actually stored in blue, green, and red order, which is a little awkward to get used to. From there, we just read the row data out one by one. We also need to make sure that we actually allocate the pixels inside of our header or inside of our image, so that's what I'm doing right now. Always free our data, and voila, that should be the absolute most important part of our code. Before we move on, we have to fix one issue with Windows. When Windows opens files with fopen, it opens it in a text mode. We need to open it in binary mode so that the actual bit data is coming out correctly and it's not being garbled or removed. We can do that with Fcontrol. Now that we've fixed the Windows issue, let's actually use our bitmap class and structs that we've written to actually load the data into our main program and then render it out with OpenGL Draw. We want to make sure that we're rendering at the actual image size, so we're going to render our OpenGL window at the pixel width and pixel height. Then we're going to loop over the pixels inside of our struct and render them out with OpenGL. We need to invert the row as we go down because OpenGL renders from bottom up, and we need to render our bitmap from top to bottom since that's how the pixels are stored. Then we can actually render the color out after we get our values pulled for what our coordinates should be, using our translation methods for coordinates to screen. And our pixels are stored in unsigned cars for colors, so those are up to 255, so we need to do some floating math to make sure that the values are converted to 0 to 1 ranges so that they'll render correctly in OpenGL. Then we can render them out as a single box using the polygon call. Of course, we're going to run into issues as well. And I forgot to actually compile my bitmap CPP file, so I needed to fix a few issues that came out of that. Some of those things included not bringing in the proper headers for us to be able to read memory, not putting in equal signs when we're reading in data, just some general compilation issues that we can easily resolve. We actually got our own error that said our div header was not 40 bytes, which is a little strange. At this point, I generally reckoned that I was not reading the file correctly into memory, and then realized I forgot to actually seek to the end of the file before I said how large it was. But I didn't actually understand this until I started to confirm this by printing out this information and debugging it by trying to print the header info. It's actually useful to do that anyways, so we'll expand upon that function here momentarily. Once the file read was fixed, we had our image. We can print more information from our headers just to make sure everything else is reading it properly, but seeing the image on the screen is probably the biggest testament to this thing working. And we can also print our div header information since it has stuff that's more appropriate for things that we want to look at, like the width and heights, row sizes, etc. Let's try to render something more interesting. Boom! There's the man himself. So we have successfully rendered a 24-bit bitmap image using our new program. Now that we've rendered the 24-bit BMP, can we render one that only has 4 bits, also known as a BMP 16? Bits on the pixels inside of the 4-bit BMP are stored a little differently. There's actually 2 pixels per byte, which means every 4 bits is actually a pixel itself. And it's just an index of a 16-bit set of colors inside of a pixel. There's not actually RGB values stored inside of those 4 bits. To pull those out, we're going to have to use some binary operations like masking, bit shifting, etc. But once we do, we can pull those bits out and store them as individual pixels inside of our actual pixel overall. I'm going to write a pixel from 16 function, which will take that index and map it to one of the 16 colors that are supported in bitmap 16s. You can find these color tables online. They're relatively straightforward. Essentially, it's a value of 0 through 15, each one representing a different color of red, green, blue, white, gray, or black. It's a little bit tedious to get the actual case statements written, but once we do, it goes relatively quickly since we can pretty much copy paste them for the upper bounds of pixels as well as the lower bounds. A little more debugging, we forgot to allow ourselves to read 20 or 4-bit colors, and once that's resolved, boom, another image that's 4-bit. So that's all for loading BMP images today. There's more formats out there, but you should be able to take this code as a baseline for being able to read BMP files and load them up on your own and support more options in the future if you need to. I hope to use this function as we make more game code in the future to load in texture files so that we can render out sprites, etc. Into our engine and into our game moving forward. Anyways, guys, thanks for checking out the video, and hope to see you again soon.